All right, can everybody see that?
Yes.
Okay. All right, well, good morning. My name is Jennifer Kitchen. I am here today to represent the IC Circuits and Systems group. That's our focus within ECEE. So today I'm going to go over a lot of what we're going to talk about is going to be the different areas of expertise and research that the professors have in circuits and systems. I guess starting with me. So I've been a faculty since 2013 at ASU. I am ASU alum also, woohoo! So I'm back for more. My specialization is power efficient electronics. And so that varies from power converters, high frequency systems. So I do a lot of RF transceivers for wireless, for wireline, for SATCOM, a bunch of different applications. Distributed architectures, now we call them MIMO. You guys, new cell phones have all of this stuff, phased arrays. So this is kind of my area. I work in a lot of, when we think of circuits, a lot of people think of either boards or silicon integrated circuits, but there's actually other technologies like gallium nitride, gallium arsenide. There's hybrid technologies where we integrate multiple different chips in the same package. So we work kind of across all of these different technologies, and we also do the package level integration. So that's kind of a little bit about me. I teach at ASU 335 more recently, and a graduate level course on RF transceiver systems. And then I've also in the past taught 433, 591, which is the sort of senior level of analog integrated circuits. So there we go. Okay, so today I hope to outline for you all what are the focus areas in circuits, basically by specialization of faculty. So introduce you to some of the faculty that we have, and then what are the applications for circuits. So I'm going to do this basically by talking about where our students get jobs. So we kind of track, as students leave us and go on into their career, where do they get jobs? Do they stay? Where do they go? I've got it's older data from about 5 years ago, but I think it's interesting on kind of the different areas of electrical engineering. So I'll talk to you a little bit about that too. So our areas are divided into 5. We've got analog circuit design, which is very, Dr. Bakalolu does a lot of this, power converters, basic analog circuits, op amps, maybe ADCs, that sort of thing. Then we've got digital and VLSI circuits, which are VLSI, very large scale integrated circuits. Then we have MEMS systems. So we have a couple of faculty that have worked particularly in MEMS. Merging devices and circuits. So this tends to be memory based more than anything. And then the high frequency RF and microwave systems and ICs. And it's interesting, but a lot of the microwave systems actually overlap with probably what Dr. Balanis was talking about. So some of those students may actually take like a 445 class to get some background to do microwave. So faculty for each area, I won't list everybody, but you can see that there are 2 or 3 faculty in all of these different areas. As undergrad so far, many of you may have had Dr. Brunhaver for 333. Dr. Kao and Dr. Chakrabarti, Dr. Chakrabarti will teach a 203 class, but typically teaches at the senior level with Dr. Kao. Dr. Fan teaches 425. Jason, also graduate level. And let's see, Dr. Ozev is 425, so you may have had her, and David Ali teaches also lower and upper level. So I think kind of you may look through this list and see you may have had 1 or 2 of these professors already and know something about them. But again, split into those different groups as much as we can. We do a lot of cross-disciplinary stuff too, right? So I can say that I work with almost one of every professor in any of these areas on projects. So if you're thinking about senior design along the way, you can think about one of these 5 areas if you like the circuits and systems specialty, but you may also end up in multiple areas. I think those make the best senior design projects, actually, the ones where you get more exposure, they're a little bit more broad. Okay. So we are located, the majority of the circuits faculty, aside from a couple that have wet labs that can't operate in ISTB4, the majority of us are on ISTB4 on the 4th and 5th floors. So if you haven't been in the building, if you ever get back to campus, and once they open the building back up to you, I recommend you go in, because this is also the space building. So we've got the really cool lobby downstairs with the Mars Land rover and the really neat images. And if you go on to, so the picture on the bottom right is the third floor, actually, it's the moon floor. So this is where we're located, again, kind of sharing it with the SESI folks, but we have quite a large lab there. We have a shared lab, which is an interesting way to run a lab. Most faculty and most universities don't share labs as we do, but that allows us to have a very large, very well-equipped circuits laboratory on the 5th floor of ISTB4. Okay, so some applications. I don't think I need to go into this too much with you because everything is hardware that we look at, right? We have circuits in basically every piece of electronics now is stuff that our group will cover at some point. If you look at these images, I always keep this slide because if you look at the images, they're old. So look at the wireless, look at the computer. I'm going to guess most people that are on this meeting right now have never seen a computer that large, or the flip phones. We had the flip phones, or even the ones that weren't flip phones, before the flip phones, they were that single piece. So I keep this because this slide was applications that I showed in my PhD dissertation. So I guess it's got some, so you can just see, I'm not that old. So you can see kind of from the time I did my PhD, these were images that were state of the art to now. And you guys know it's state of the art now. So you can just see the progress, right, in that time frame and how quickly we've evolved in electronics. And so our group, that's what we try to follow, right? We try to do it with our courses. We try to do it with our research. We are ahead of that progress, right? We're trying to be 5 to 10 years ahead of what industry is doing. And we try to prepare our students such that they can come out and immediately make contributions to, circuits in various electronic systems. Okay, so our courses. So here's how it works. Many of you may have already taken 333 and 334. After that, we get into circuits 2, which is 335. And then from 335, so 335 is like our gateway course, okay, for the circuits area. From there, we start to separate our courses out into digital and analog because there's too much information to combine digital and analog in the same course after 335. So 335 is teaching you the basics of both digital and analog, you're scratching the surface. And then we dive down into digital or analog. And we've got at digital, we've got 425. It's also a 591 course at graduate level. And at the analog side, we have 433. Again, also a graduate course, 591 offering. And then once you take 425 and or 433, you can start going up, right? So if you ever pursue a graduate degree, or if you're kind of ahead of the game, or if you're doing a 4+1, you can continue on into the 500 levels, 523 and 525. And then once you have those 4 core courses in both analog and digital, you can go into a variety of special topics. So that's where we get into RF circuit design, switch capacitors, oversampling converters, A to Ds, modeling. There is a constructionalist approach to microprocessor design. That was a 498 and now a 598. So all of these things kind of build on these circuits courses, right? These core circuits courses. So we've got a lot of offering. 598s and 498s, just for your understanding, are courses that we call them special topics. So they're kind of the hot topics of the time. It's not guaranteed that they will be offered every semester or even every year. They're developed by various professors, and we don't guarantee them. It's dependent on resources. So if you have a 498 course you come across and you really think you're going to be interested in and benefit from the course, take it while you can, because you don't know if it'll be around again, next semester or next year. Okay. So new faculty, we always put this up. So in the past few years, we've had 2 new faculty come into our group. Dr. Z, don't ask me to say his last name. I have no idea how to say his last name. So we just call him Dr. Z. And Dr. Fan. Dr. Fan is more in architecture and circuits for microprocessors. Dr. Z is all RF, millimeter wave, very, very high frequency circuits, borderline to terahertz. So I'm going to go through and kind of, some of these slides are very specific professors and what they're doing. And some of these slides are more vague because there are multiple professors that work in an area. So I kind of want to go through and sort of talk to you about the different areas more with a focus on the research aspect, because we find that professors bring some of that research into their classroom, right, for learning. But also this is what will, maybe when you guys are thinking of, do I want to pursue circuits and systems? These are some ideas of what you could be doing, right? Whether it's in industry, in research, in a graduate program, whatever that may be. So Dr. T, he does terahertz imaging systems. So for a variety of applications. So terahertz, remember, that is light, basically, right? We're so high in frequency that we cannot, it's just difficult for us at this point in time to even create hardware, right, to process these things. So when he says terahertz above 500 gigahertz. So if you want to compare that to what your cell phone runs at, 1 or 2 gigahertz, right? And we already call that high frequency. So imagine now we're at like 100 to 200 times that in frequency. So terahertz has been said to be very good for imaging. And so he's doing it for imaging of various things like cameras, like like underneath, trying to use it for things like looking underneath tables, security in rooms, very close distance where you have a lot of reflections in a room and it can track that. So almost becomes like a sort of geolocation and you can then image with that. And then we have more like we're getting kind of close to, we're kind of coming down in frequency to more what we call millimeter wave. So below 500 gigahertz, this might be in the 100 to 200 gigahertz realm. And Dr. Z works on that. He also works in imaging, but he focuses more on the hardware for it. So not the methods for how we image or the applications, but more how are we going to get the hardware, the circuits to do that. That's where he builds integrated circuits on silicon germanium substrates or something like that. And then he measures them, tests them, he finds applications for them. He also does some space stuff because we think when we're thinking of deep space exploration, a lot of sensors, they're looking at very, very high frequencies for sensors. So he's exploring that area too. And then we go into, so that's kind of the terahertz millimeter wave area. And then we have VLSI research. So VLSI covers a large range, right? So we've got VLSI, again, that stands for very large scale integrated. And it could be integrated circuits, which is shown on this slide. So microcontrollers, microprocessors, large arrays of processing, right? Memory. And there's a variety of areas that professors work on in VLSI. One big one is radiation hardened VLSI, because with the way that the space industry is going right now, everything needs to be radiation hardened, right? In space, we have radiation. But what we're finding is a lot of the microcontrollers, microprocessors they're not reliable and they don't survive radiation. So there's a big study on how can we make them radiation robust? How do we make them most efficient and that sort of thing for ultra low power, harsh environment. We've also got VLSI for security, of course, microcontrollers, cache, processor units, and that sort of thing. So more particularly, kind of one of the interesting research areas within the VLSI community is neuromorphic computing. We've got a couple professors working in neuromorphic computing. So basically that's saying, okay, our standard way of doing microprocessors using, we call it, so a long time ago it was, and still now, it's FPGAs, right, for flexible computing. And then you build an ASIC, which is very specific. That's like what Intel does, right? An ASIC can be, it's CMOS nowadays, right? So we talk about like Intel starting a 7 nanometer fab in Phoenix. Well, that's a CMOS 7 nanometer fab. But there will come a point in time when we feel that we just can't get enough computing power out of a microcontroller as we know it in CMOS. So there is this push to think of other ways that we can do computing, and that's called neuromorphic computing. So they study the brain, neuroscience, they study nanoelectronics, basically different types of devices, like nanowires and that sort of thing, and see if there's things that we can gain from the neuroscience and use that for computing, right, for electronics computing. So this is beyond what we call beyond CMOS. We also look at architecture. So Dr. Brunhaver does VLSI architectures. So thinking above the circuit level, how do you orient computer systems to best do computing, right? How do you share resources? How do you share compiling? Where are the bottlenecks in computing, and looking at it from an architectural perspective. So in coursework, like I said, he had previously taught 333, but he has this constructionalist approach to microcontroller design, and that focuses basically on this slide in terms of coursework. Okay, and then we have Dr. Fan. He does all layers. So he's kind of starting at the hierarchy that Dr. Brunhaver does. And then he builds down from there. So from there, what do our circuits, our blocks look like? And then how do we actually build circuits, right? To kind of support those different computing architectures. And Dr. Fan, like I said, he's teaching 425. In the future, he may do a 334 class. So some of you, if you take the online 334, you may have him. And then Dr. So we talked about neuromorphic computing. That is different from this. That's basically studying the brain, right? And how we can do computing. This is neural networks, also taken kind of from that idea of how we learn, right, as humans, a neural network, but building it for machine learning. So we have a couple of machine learning courses in the ECEE department. So if this is interesting to you, I recommend you look into the machine learning, but basically efficient hardware, and then how do we cognitively adapt that hardware to learn, right? And how do we build those in hardware, those systems? Dr. So also does power management circuits, very low power, low voltage, very highly efficient power management, because when you design all of these neural networks and computing systems, you need voltage regulation to them, right? You need power coming to them. And so it ends up integrated in the same integrated IC or on the same chip. So he also designs those for these systems. Okay, and then we've got bioelectronics. This is always seems to be an interesting one, I think, to a lot of people, because you get that attachment to kind of humans, right? So Dr. Blaine Christian does, she actually works a lot with clinical trial medical doctors. And she's looking at how do you do point of care diagnostics. So you've probably heard of like machines that you could bring home and actually diagnose yourself for different things. She's looked at cancer. She's looked at nervous system issues. So she's trying to kind of look at the chemistry of human, our human anatomy, with integrating that with electronics to do the sensing for various forms of disease. So her lab is in Goldwater Center. I think she also has one in ERC, in the ERC building. On that kind of same wavelength, literally. We also look at MEMS systems, and MEMS, again, for sensing brain function. So if you think about your brain you've probably heard of EKGs, right? So some very, very small pulses come out of the brain, and those small pulses control different things. They can tell us different things about humans. And right now, the only way that we can get brain functionality or understand brain functionality well is actually embedding probes into the brain, which is very invasive. So we don't do it very much. So there's a very big push for non-invasive tracking of brain signals. And I'm talking the very smallest ones, right? For early detection of stroke, control, haptics response, all kinds of stuff. So we need sensors to be able to do that. And so we're looking at MEMS are basically taking small movements, right, mechanical structures, and converting those to electrical signal. Okay, on that same, for also using MEMS really for sensors, we also look at it for earthquakes, atmospheric, fluidics, a lot of the geosciences too. So that's another kind of application of MEMS and those sorts of sensors. And then all of these different things, again, can kind of go back to radiation hardened electronics, because if you're using any kind of communications, any kind of electronics, any kind of microcontroller in space or for instrumentation or for nuclear facilities, they need to be rad hard. And so you can kind of apply, you can kind of take any one of these sorts of areas of circuits and then say, can I make them radiation robust, or how do I make them radiation robust? So this kind of applies to basically most of the stuff that we've already talked about. And then finally, emerging devices and circuits. So basically, how do we create an entirely different kind of device, memristors, wires, how do we store memory without using a typical transistor as we know it, or a CMOS device or an NMOS device? So memristors is one thing that Dr. Yu was looking at. And then again, that brain-inspired neuromorphic computing. So basically, alternative ways to make devices, completely different from silicon ICs. So I think that kind of summarizes different areas of research. Hopefully I threw some stuff out there that might kind of get you guys thinking. If you're interested in any of these things, that's the area of circuits and systems, right? So those core classes that you would have as an undergraduate would allow you to pursue these different areas.
Hello. Yeah. Bring my headphones real quick.
Oh, there we go. I think Cheryl's on that. Okay. So maybe more interesting to you is just kind of where do we find jobs? So I thought this was interesting. This is in Arizona in 2016, so a little bit dated now. It was the top 100 companies in Arizona. So if you love Arizona like I do, if you want to stay in Arizona, you think about job marketability, right? And if you're going to be able to keep a job in the state. And so you can see, I just pulled from that top 100 companies that are directly relevant to circuits, and a lot of them ICs also. So you obviously Intel, Raytheon, Honeywell, and you can see that's the number ranking, one being the largest. Boeing, IBM, Freescale, which is now NXP, Microchip, Orbital. So a lot of these, you've got your category, but all of these do circuits hardware and systems hardware. So right there, you can see there's a lot of job potential in Arizona if you're interested to stay. I also liked Fortune magazine did, this is the 2017, they come out with one every year. They don't change too much actually, but they did a kind of a survey of best top 50 companies to work for. And so they've got different, I guess weightings, they've got different parameters they look at. They've got, job pay, right? They've got benefits, they've got just general atmosphere, they've got, the little perks that you get, they've got paid time off, all of these sorts of things, and they roll them in to one, the actual quality of the job, right? Research and innovation, all that sort of stuff. And they roll it into one number, some figure of merit, and then they compare companies. And so from that, I took 6 companies that are very relevant to circuits and systems. Again, so if you guys take 335 and the upper level, you will know Cadence, whether or not you want to, but it is a very good company to work for. Cadence Design Systems, again, very, circuits, hardware, you have to know those circuits, right, to design or to develop process design for Cadence. Google, Intel, Qualcomm. Intel, Qualcomm actually have facilities in Phoenix, right? NVIDIA. So it's kind of showing you that, if you have this specialization, you can work for some very good companies, meaning good companies from an employee perspective. And then, we try to track kind of some of the places that our students go when they leave. And you can see there's a big list here. Intel, Qualcomm, Broadcom. Qualcomm and Broadcom tend to be the people who want to do more high frequency. Apple, I've had quite a few students go to Apple lately. Silicon Labs directly recruits from us. Texas Instruments directly recruits from us and has actual scholarships too to ASU. Qorvo, it's located in Phoenix. Medtronics, right, also located in Phoenix. So you can see there's a variety here, again, directly applying to circuits and hardware, and of course, government labs and startup companies. But these are some of the biggest ones our biggest employers, I guess, for students leaving the circuits group. So you probably recognize many of these companies from their products. Okay, and then in this is dated 2015, 5 years, well, in the grand scheme of things, I guess not that dated, but there was the Electronics Engineering magazine so you can see these are pictures I took from the magazine, right? Had a survey of electrical engineering careers. And I thought there were some interesting just points to this. One was, this applies in general, right, to electrical engineering. But you can see just looking at the different states, work locations, that Arizona had a high number of jobs, right? If you look, of course, California and Silicon Valley, it's going to be large. But you could see that, Arizona and Texas, Colorado, nearby states had also quite a large share of the electrical engineering positions. What I also thought was interesting is if you look at number of years in the profession, you can say, that we have some under 20, right? These are folks that are typically right now doing their degrees. But there's a big gap in the middle, from 20 to 40 years of experience. We don't have many people, and 40 plus are all going to be retiring soon, right? If not already. So you can see that we've got attrition from engineers retiring. We have this kind of gap in time where not many other engineers are becoming very senior. And so if you kind of look at that cycle, you see that as a starting out engineer, you have a very good job market. We still need the engineers, right? And so you can just see that we've got a very high attrition from people, leaving this industry, and we need to fill those jobs. Typically that means, right, that you've got a large demand, and you'll be, for you, assuming that, you do reasonably well in school, you have a good chance to get a good position in engineering, electrical specifically. I also like this. It was a compensation breakdown by industry. So you can see the different, just avionics, medical electronics, some of these are more use case based. So they're not design in medical electronics necessarily. They're maybe putting together a system for it or selling it. But you can see by looking by industry, ICs and semiconductors, which is the circuits area for sure, is one of the highest compensated jobs. Again, high demand for it. And you need these very specific courses, right? You need to complete these courses to have some understanding of circuits. So also well-paid positions. So if the research stuff doesn't motivate you, maybe, the financial aspect motivates you, right? And then by compensation breakdown. So this is just looking at the various location states, right? And then the various areas of, or the various average compensations in electrical engineering by state. Again, Arizona's not too bad, right? Somewhere in the middle. It's not going to be as highly paid as the coasts, but the coasts are also more expensive to live. But we're not doing too badly either. And then you can see by years of engineering experience at the bottom. So I just thought those were some interesting facts. And I will end there. Thank you for your time. I hope that some of you guys that are on the borderline of what you may choose, maybe this persuades you one way or the other. If you have any questions about this material or just general questions about what we do as faculty or what you may end up doing in your career, feel free to email me. I had my email, I don't know if Cheryl can share it, but I had my email on that first slide to kitchen.jennifer@asu.edu. You can find me in the directory and feel free to email me. You can say you came to the Pathways course and you had questions. I'd be happy to answer them if I can.
Yeah, Dr. Kitchen, I just, a student had asked privately about where the recordings will be posted, and I put that in the chat. So students would like to copy that link from the chat. And we did have a question from an online student who's, luckily a lot more online students have attended these since we're on Zoom. Yeah. And he was, or this student was curious about advanced class options for online students to access, and if online students often get access to advanced research with our faculty.
Yeah, okay. So very good questions. Advanced classes of 433 and 425 are both taught online. But be careful because they're taught online once per academic year. So we have 425 online one semester, 433 online the other semester, and we alternate. So if you're going to take the senior level, make sure you get the right semesters, right? You plan for the semester. In terms of the 500 level classes, if you want to be, so there are some undergraduates that ask for permission to continue to a 500 level even as an undergraduate. And they are also offered online. So 523, well, I should say the line. 523 is offered fully online. 525, we have a GOE option. And I think a push to offer that fully online very soon, but I believe online students can, I don't know, that might be a question maybe for you, Bob, about the GOE.
Yeah, I know we're more and more is offered online. It's not an exact analog, but we're getting there. And then in terms of research, I know that some students have this similar to how a Tempe student would develop a relationship with a faculty to do research. Online students can too. Do you have any comments on that, Dr. Kitchen?
I do, yeah, very true. And I would actually say that we have a very, because in circuits and systems, we do a lot of simulation-based work. So a lot of our work, right, is first finding architectures, literature, simulations, right, whether they be system level simulations or circuit level simulations. And now we've got a really nice setup for access in research for accessing those simulation tools remotely. So a lot of that research can be done remotely. Now we always have in hardware the issue of measurement, right? If you actually have to get into a facility and measure something, but you might be able to organize your research such that you don't have to measure, or you work with another student that's in person that does measure. So I've worked with a few senior design groups that are all remote. And they've done some fun stuff. So they do a lot of their simulation, that sort of thing. And then one student actually went off and built something at, his house or facility, and another student built the other part of it. And so they've managed to actually get around. You have to plan a little bit more, but they were actually managed to actually get some hardware built too. So if you're thinking about senior design online, again, you can fairly easily accommodate that in the circuits area because we do so much at a simulation level.
Yeah, and thank you. I'll put the general answer to developing those relationships would be to look at our faculty bios on our website, and I'll post that in there, and then you can know who to contact to see what sorts of things or where your interests would line up with what our particular faculty are doing. So I'll share that in just a moment. Another question here was from Tom, and he's asking what a good specialization would be for instrumentation.
So I guess I would ask what kind of instrumentation. So if you're talking large scale instrumentation like high particle physics stuff or nuclear, that sort of thing, then I would definitely say maybe stay more. I mean, you still need to take your basic circuits classes and stuff, but stay more on the system side of things and the radiation hardening. If you're really going for the big instruments, they tend to all require some kind of, I say radiation hardening, extreme environment. So they all require some kind of, odd, unique environmental concern, right? Whether it be radiation and or temperature and or reliability, robustness. And so you could, from a kind of more, maybe more of a research aspect, so not so much coursework, I would look into that.
Okay, and then another question here is about job opportunities. Would your opinion here to be competitive, would it be better to concentrate in analog, digital design, or both?
Okay, so the both is called mixed signal design. And yes, it gives you the most flexibility. So mixed signal designers, they can get jobs either digital or analog, but they will, at an undergraduate level, mixed signal design is the best way to go, I would say. Take both the analog classes and the digital classes. You have the most breadth there. At a master's level, if you focus on one very well, meaning take the entire digital course path, right, and take all the digital courses, you'll do very well. Or the same for the analog, right? If you stick in one path, you'll be fine. The issue is if you take a hodgepodge, right, at a graduate level. So if you take one class here and then one over here and then one over here, then you're not good at any one thing. And that might actually be to your disadvantage. But as an undergraduate, I would say do both. If you have the ability, if you have that ability in your schedule to do both 425 and 433, right? Let's say I would do both, because then at a graduate level or at an industry, you can do either, right? You can then end up specializing in either.
I think we got the questions here. Are there other questions out there anybody has? Oh, we got a long one here. So I don't know if you can see this too. So thank you from Nathan. He currently works in the FAA as a systems specialist. He works in radios, navigational aids, and seems as throughout the aviation equipment, such as radios, radar, et cetera, is still technology from the 70s. Do you happen to know anything on the horizon for RF systems in this area?
You should look at the guys that are now providing the radios for, so you may be familiar with like JTRS stuff or the MIDS. So radios for military applications, and you can see the progress that those had made recently. So I know, like, I used to work for Viasat, so I was working on those radios. So I know Viasat has made huge progress in that area, as well as some of the other companies that support that effort. And so I feel like, yes, you will get there for sure. And I feel like that trajectory will probably follow. It seems like aviation's always later because of reliability concerns, but I feel like that will follow a similar path to how these man-pack radios have gone. So yeah, they will get smaller, I think. The technology is there. It's the willingness for that community to adopt those techniques and qualify them, right? As well as obsolescence of parts. So over time, it has to be done, because that those 70s technologies will go out of date, and you're not going to try to build the same thing again, right? So it will happen, and I see it happening the same way it's happened with some of the military radios.
Okay, and then Chris is asking, when you say systems courses, would 425 and 433 be considered?
Those are circuits courses. Those are circuits courses. So we don't offer pure electronic systems, right? We do it through combinations. So if you want, so, you know, for instance, you may take signal processing courses for the system level signal processing, and then you may take circuit level courses, 425 being digital, 433 being analog, to make up the circuits portion, right, of a system. But in 433 and 425, you learn, for instance, in 433, op amps, operational amplifiers. I mean, if you want to call that, it's not, it is a type of circuit, right? But it's multiple circuits that make up this operational amplifier. So yeah, systems, yeah, it's a vague word, I guess. In research, we really do systems. So we will put together an entire radio system, right? And we'll do the signal processing, and then you do the circuits, right, for the radio. So in that way, these various courses are pieces, I guess, to build that system.
Any other questions out there? Thanks for contributing questions, everyone. We had a student comment that he agrees with you that mixed designers are very much needed. So thank you for seconding that.
I would agree with that. I don't think you guys can probably comment as advisors, but you know, our students end up doing great things. So
yeah, and to Nathan's point, I just want to throw in there, I'm not an expert in this, I'm not an engineer, but questions like that often result in students in their program having fun because they have a specific context to apply it to. So that's fun. I encourage everybody to kind of think that way and think of how you can apply it, even if you don't work in the area. So thanks for that question. That was fun. Ooh, I think I got one more here. Thank you all. So from so thank you. Thanks for joining us. Yeah, I think we had about 75 or so at the top. Cheryl, is that right?
I think that the high was 77.
Ooh, that's fun.
That's awesome.
That's one more question. So Chris says, for good circuit designers, is signals or electromag more important?
Depends on how high in frequency you're going. So electromagnetics is required for very high frequency circuits. You're going to need to know your EMAG. So if you, so in the EMAG, I shouldn't, you know, maybe not the 200 level, but in the 300 and 400 level EMAG courses, you learn tools. So design tools, in essence, you may not know that actually at the time you're taking the classes, but you do learn design tools that will help you design the high frequency circuits. So you actually, you know, if the high frequency, you almost need both. That's why high frequency becomes trickier. At the lower frequency, no, circuit designers do not need EMAG. I can really be honest. We don't teach it in our courses, right? In our course flow. But if you try to specialize in certain areas like high frequency circuits, you'll need the EMAG. I see Brian has a focus on solar cell, renewable energy production. There are classes on solar. Dr. Rodell teaches one, right? Not under the circuits group, but in electrical we do. There you go. 498 also has, King said 498 has solar cells. Yeah, that's the fabrication of solar cells, right? So more from the making, you know, level. But Dr. Rodell does one more from a system level and an ethics and installation, and he talks about like kind of the broader topics.
I'll put Dr. Rodell in the chat so you know who that is.
Yeah.
Crazy question from Tom.
Tube deck. Oh, that's not that old. Jim Aberly, Dr. Aberly loves that topic. So if you are interested, yes, yeah, in musical equipment, if you are interested in that, talk to Dr. Aberly. He really just has a general, I don't know, he's got an affinity for that. So, and I agree, it's under, you know, with new technology, we kind of pass over that stuff, but it works well. So yeah, you can try talking to him.
Cheryl, who's fixing, who has the office with all the fun vacuum tube equipment?
That's Dr. Aberly, I think. He used to have in there.
Dr. Spanias has some vintage radios in his office that I covet because I also like to collect vintage radios, tube consoles and things like that. And I know that Dr. Aberly has had a radio club, and Dr. Michael Goril has helped me in fixing some of my old radios that I have in my office. So there's a lot of people in this building who love that old technology.
Very neat. Yeah, so they're in the circuits areas, it tends to be most of the conferences that as circuits faculty we attend, there is always a ham radio club.
Yes.
So a lot of the conferences we go to, they'll have like a ham radio section, you know, or a club. So that's kind of fun if you guys, if any of the students get
Yeah, and Tom, we did have a student who unfortunately left the master's program because he was into the same thing, and he now works for Fender developing vacuum tube amplifiers for guitars, so guitars and basses. So it's still out there. There is definitely is there is industry. I think I would guess that the people in that sort of niche area probably aren't recruited at the same salaries of people who are going to places like Intel, but it's the most passionate people are out there doing it. So I forgot his name. I wish I remembered, but he left our master's program to go work at Fender, and he was very excited.
So I see some questions about power electronics from Patrick. Yes, analog classes are very relevant to power electronics. So if you take, that's what I do actually, I do a lot of power electronics. So if you take the class by Dr. INR, it's called Power Electronics, I think, something like that, right? 470 something, 472, I want to say, maybe something like that. It is that is a class that our circuits students go and take if they're interested in power. That will teach you the system and the architecture and the feedback and how we compensate and make things stable and that sort of thing. But then to build that system, you actually need the circuit. So how are you going to do the feedback loop? Well, you need op amps. How are you going to control the power stage? We need drivers. And this is all circuits. That's pure circuits. So yes, very, very relevant to power electronics. Programming skills are great. The Python class has had very good feedback, well recommended. I think it's taught by Millman now, right? And I think programming skills in general are wonderful to have. So I think you can apply that to any position, circuit design also being one of them.
Dr. Harton also teaches the 498 version of the Python.
Okay, yeah, all right.
So it's out there.
It is, yes. Yeah, Anthony, I kind of agree. You got to have something, you end up programming for something, right? Even the pure analog digital hardware people, we program FPGAs to test our hardware, or we have to program a script to automate our simulations because we've got 10,000 simulations we need to make. We're not going to do that manually. So there's always some bit of programming in there. Yes, control theory is important. Again, if you're going to design more complex, so that is system, right? That's the system aspect. So I would definitely agree. You've got all these different circuits, but before you build a circuit, you need the system level. And that control theory can very much help with that. We had a few students do control theory and circuits and ended up doing full rebuilds of automotive cars, their own cars in some cases. So they were very interested in that, doing the control theory and then doing the circuit level hardware, right, for that. So we find that a lot of the electrical engineers that don't want to do quite mechanical, they want to stay on the electrical side, but they combine that control theory and electronics and they end up in automotive areas. I don't think you need much programming skill. I believe like a 333 level might be enough for the 498 Python. But I think those prereqs are probably listed online.
Mm-hmm.
Yeah, digital signal processing is great. 407 is a good class. I think you need 352, right? Is that the one that precedes that before you can take the 407? So a lot of people who take 433, 425, 407, they try to combine those sort of things together.
To Steve's question, I don't think we have an electronic link to data that Dr. Kitchen showed about career stuff, but I'll put the BLS link that I'll share is general and it's not as regional specific that she posted. But you can also follow up with the Engineering Career Center. I know they have data on region specific stuff, but I'll share my the go-to link is often the BLS site, and that has some state and area data in it.
I just posted the prereqs for the Python class, the 498. But you guys can just look it up in the class search. If you just go EEE 498 and click on Python, it'll drop down and you'll see this short description plus the prereqs.
We should do a last call for questions. Thanks, everybody. That was very engaging. We're noticing that people are more apt to ask questions and talk. So
Yes.
get some thank yous from a couple folks. So thank you for coming here. This was fun.
Yeah, thank you all. I hope I see some, well, I see some, I think there was a name or two that I saw in the chat that I recognize in 335. So I think a couple of these guys may already be in my class, but if not, I hope I see or hear some of you in the near future.
Definitely. Thank you so much for doing this, Dr. Kitchen. We appreciate it so much.
It was a pleasure. Have a good afternoon or good day, all.
Thank you.
Sure.